Hi everyone, this is the NEO-CATH project, a smart urinary catheter designed to enhance patient care and comfort. My name is Kushi Praveen. I'm a biomedical engineer and the team lead. Urinary Foley catheters are one of the most commonly used medical devices in a multitude of settings, both in hospital and out of hospital care, and they are designed to drain urine from the bladder and into a collection bag. Now, these types of medical devices are used by millions of people who are unable to independently urinate. However, there's significant challenges associated with these catheters, such as painful insertion, inflammation, irritation, and infection, which then can lead to more severe issues such as increased hospital stays, costs, and even death. One of our main goals is to limit the number of catheter-associated urinary tract infections, also known as CAUTIs, which occur when bacteria develops on the catheter surface and eventually develops into a protective biofilm layer that then protects the infection from antibiotics, thus making it antibiotic resistant. Now, these types of infections are considered preventable. However, for 15 to 25% of users, that's not the case, and it can cost them anywhere from $1,000 to $5,000 to treat. So, what are we doing? Our goal is to develop a smart urinary catheter system that has the capabilities of reducing pain and inflammation through our drug delivery system, preventing infection through our advanced electroceutical technology. We are also continuously monitoring temperature and pH values of the patient and creating a mobile application so that healthcare users can easily access the data from our catheter.
Hi, my name is Cassidy Little. I'm a biomedical engineering major, and I was the mechanical lead for our RCA design project. To create our NEO-CATH system, we took a standard 3-lumen Foley catheter and modified it to meet our therapeutic needs. We took this catheter and we integrated 2 temperature sensors and a solenoid on the outside, wrapping the solenoid around 4 inches of the catheter system and putting the temperature sensor on either side. With this setup, we dip coated it in silicone to encase the electronics and provide a smooth surface for our later dip coating of the drug solution. Here's a video of our full catheter design, including the catheter, urinary bag, and the Arduino connected to the sensors. Our 3-lumen are for irrigation, urine drainage, and to fill up the Foley balloon at the tip of our catheter that keeps it securely in the bladder. Here we're going to point out the tip of the catheter where the urine enters the catheter and where the Foley balloon is located. Above that, we have our 2 temperature sensors in these 2 locations, and in between that, our solenoid for our EMF strategy. All of these wiring and sensors are encased in silicone. Here we have our urinary bag and our pH sensor, which is at the other end of the catheter. Our 2 temperature sensors, one on the tip of the catheter in the bladder and the other about 5 inches distal at the opening of the urethra, will monitor changes in upper and lower temperature as well as the temperature variation between the 2 temperature sensors. We also implemented a pH sensor in the urinary bag to track shifts in urinary pH. With the monitoring of shifts in pH and increases in temperature and temperature variation, which have been shown to be early indicators of catheter-associated urinary tract infections, we can have timely detection and early intervention to stop the risk of infection and complications due to this.
Hello, I'm Cameron Balderrama, an electrical and computer engineering major and the electrical lead for our project. The overuse of antibiotics and the formation of biofilm colonies causes patients to develop bacteria that is more resistant to typical antibiotic treatment. To counter this, our system has incorporated an electroceutical strategy. Catheters are a direct connection between our vulnerable insides and the outside world, so CAUTI-causing bacteria is inevitably going to develop on the catheter surface. However, it takes a few days before it reaches a dangerous level. When current runs through a wire, an electromagnetic field, or EMF, is generated around this wire. And our studies show that the growth rate of bacteria in certain EMF environments is reduced by 22%. This allows healthcare professionals time to replace catheters before the CAUTI is created. We can generate the bacteria-fighting EMF in our catheter by tightly wrapping copper wire around the drainage channel of our catheter and connecting it to a Arduino.
We have 4 AA batteries powering everything, and it is directly connected to the Arduino. We used a pre-made pH sensor with the board here, and it is also directly connected to the Arduino. The temperature sensor is actually a thermistor inside of our catheter, so it needs a voltage divider here to read the temperature. And then our EMF generator, the initial signal to create that EMF is created through a DAC and op-amp combination there.
Hello, my name is Inka Hussain. I'm a software engineering major. My name is Aria Castro and I'm also a software engineering major. And the primary goal of our NEO-CATH application is to provide support for healthcare patients, healthcare providers, and hospitals. The primary users of our app, which are healthcare professionals, will have the capability to view live updates of patient readings, be able to monitor and analyze pH and temperature trends, as well as combat early signs of infection through an EMF controller.
The way our application works is that the Arduino collects data from the sensors and sends it over to the backend server, which stores it in our AWS database. It also is displayed via the front end through the application, which is this one. Here we are able to see how data is graphed over time, and we can filter it throughout the desired time range. We are able to see a summary of all the patient readings and how it's updated in real time. Notifications are also generated in real time according when a reading falls out of range. You can turn the system on and off, and then you can allow healthcare providers to view all of the patient information.
Hi, I'm Caitlin McKnight, a biomedical engineering major and the procurement lead for the NEO-CATH team. Our strategy for combating the inflammation and the pain that comes with the traditional catheter usage is by using a drug coating that contains ibuprofen and dexamethasone. Ibuprofen is a non-steroidal anti-inflammatory drug that is used as both an analgesic and anti-inflammatory agent. Dexamethasone is a powerful steroid that is used for its anti-inflammatory properties. With the combination of both these drugs, as well as a PLGA polymer coating, we can create a drug coating that delivers over a long period of time in order to reduce inflammation and pain through catheter usage.
As seen by this graph here, we were able to verify our drug delivery results and ensure that we did not deliver an unsafe dosage of drugs at any point to our patient. This result is also consistent with the literature that showed the degradation of PLG over time, which is the mechanism that allows the drugs to be released into the system. We were given a total of $4,500 to complete this project. We spent a total of $2,627, leaving us with a remainder of $1,853. This meant that we were able to conserve a lot of money while still buying all the parts that we needed for our project. The most expensive portion of this project was the drug delivery system. The next most expensive portion was the EMF, followed by the actual catheter itself, then the sensors, and then finally our team t-shirts. The final integrated cost of our prototype will be around $30 to $60 when it is made commercially available. This is more expensive than the traditionally commercially available catheters, which cost around $10 per unit. However, this is made worthwhile due to the fact that we are able to prevent infections, which are costly in both time and money for the patient and the provider.
We'd like to thank and acknowledge our sponsor, Dr. Slepian and the University of Arizona College of Engineering for providing us with the necessary tools and resources for us to successfully achieve our goals of developing a smart urinary catheter system that not only can prevent an infection, but also monitor the infection's progress. Thank you so much.